what are we going to do? We're going to do theory, as Gary promised. Then we're going to talk about optimization for gliders and then for powered gliders. I am not going to go into motor selection, battery selection, everything else. That's a whole nother kettle, right? I'm really focused in this on wires and connectors and powering receivers. That's the talk. And so you can't really have this talk without talking about what goes wrong. And it'll be obvious when we get into the optimization that it's not very critical unless something goes wrong, in which case all of these things that seem like you've got wires are more than big enough suddenly don't seem so big. So with that intro, let's do theory. So Ohm's law, volts is represented in Ohm's law the way I learned it, which is the correct way, as E. Current is I, resistance is R. The units are volts, amps, and ohms. Obviously, you can have milli and kilo and all those. I assume you know kilo is 1,000 and milli is 1,000th. Power is measured in watts, and Ohm's law is voltage equals current times resistance. Just that simple. If you want current, that's voltage divided by resistance, basic algebra. Power is voltage times current, or by substitution with Ohm's law, current squared times resistance. And those are all the equations we need for the whole rest of everything we're going to do here. And I'm not going to go through, sort of exhaustively and work every problem because this is being recorded. You can just go back and look. So a simple circuit has a battery, single cell, 3.7 volts. You probably know why I picked that. If I had a 10 ohm resistor, the current following this equation would be 0.37 amps. And the power would be 1.37 watts, which has to go somewhere in this circuit. Assuming this is a perfect battery, which we'll get back to, that is heat in the resistor. So the resistor gets slightly hot with 1 watt of power. A old incandescent light bulb's 100 watts. You can't touch it. A modern LED replacement is 7 watts. And that's a little warm, right? Just to give you a sense of what a watt is. And so let's talk about battery capacity for a second. What I have on the right is a discharge curve. So it shows the voltage versus the capacity. In this case, it's roughly a 2,000 milliamp hour battery. That curve changes shape depending on the chemistry. Lead acid batteries have a different curve than nickel cadmium. And if you wonder why you have to have different chargers for different kinds of batteries, it's because of the shape of that curve. That could be a whole nother talk. Energy is power times time. So watts seconds is joules. People talk about watt hours. So instead of joules, and watt hours are convenient, if not sort of standard physics terminology. Those two things don't depend on voltage. Joules is joules, watt hours is watt hours. All of our batteries are in milliamp hours, which is not strictly energy the way a physicist would do it, but it's super practical. So it's milliamps times hours, you get capacity. If you wanted to get energy back, you'd have to multiply by voltage, which we'll end up doing later in this talk.
John, there's a question in the chat. How does the shape of that curve change with the C rating of the battery?
I'm glad you asked. Before I answer that question, the reason for 3.7 volts being used in all of these calculations and by a lot of folks doing averages is you can see that's sort of where the battery sits. If you do an integration by I, and if you did it more mathematically, 3.7 is kind of a good average voltage, but it really matters like where you decide to recharge your batteries, right? I don't like to let my batteries go more than about 60%. So anyway, 3.7 is the number we'll use. Here is a typical unspecified cell at different currents. That was the question, right? And so what happens is the voltage drops. And other stuff happens we're going to talk about when we get to internal resistance. But basically what happens is the shape of the curve is the same. Mostly you can see at the left edge, it's a little different. And at the right edge, things cut off fast. The cliff gets sooner with higher currents. So higher currents are lower. The amount of current you can get out of a battery on hobby batteries and actually even non-hobby batteries is a C rating. It's kind of a non-unit thing, but again, it's super convenient. If a battery has a 10 C rating and it's 1,000 milliamp hours, that's 1 amp hour, so you can get 10 amps out of it. So what's that rating mean? That is a loosey-goosey safe discharge rating. In the hobby field, those are highly inflated. So if I'm serious, which in this conversation we usually care more about powering electric motors than radios, but it still matters for radios. I divide by 2 or 3 depending on the battery manufacturer and my history with them. When we get to safety, though, that C rating is conservative. If you short out a battery, it will at least give you the C rating, if not much higher. Any other questions?
Not so far.
Internal resistance. So Gary's little picture showed a way of thinking about voltage and current and resistance. Water analogy for this is super useful. If there's a water flowing through a pipe that's got a restriction, that's kind of like resistance. The amount of water flowing through the pipe is current, and voltage is, if you were doing water pressure head, how much water pressure you've got. So people talk about internal resistance of batteries. And again, for receiver batteries, you almost never think about it. We'll talk about why you would want to in a little bit. A good healthy battery, typical internal resistance for a lithium polymer is like 0.005 ohms. And if it's a 3.7 volt battery, and we're using the same example as before, 0.37 amps, then the battery is acting like a resistor, a very, very low resistor. And so the power dissipated is 0.7 of a milliwatt, or 0.7 of a thousandth of a watt. So nothing to be interested in particularly. I had to change that to a variable potentiometer because, strictly speaking, the voltage is not quite, wouldn't be 3.7 if I left my 10 ohm resistor in there, because I've got 2 resistors now in series. But to keep things simple, I just said, well, adjust it so the same current, just so we can talk about one component at a time. If you start talking about power systems, and just to go to an extreme power system, this isn't a typical, this isn't like a 5J power system. This is more like a helicopter power system or a big scale model power system. If you're pulling 60 amps on a 12S system, that 12S system is still 0.05 per cell. Now it's 0.06 ohms, but 60 amps squared is a bunch. So now you're talking 216 watts. And that's, if you do that for very long, your batteries are going to get hot and get damaged. And if you fly an aerobatic helicopter at these kind of powers and you land, you put your hand on the battery, it will be warm. The way to think about the internal resistance is like a clogged filter. The older the battery gets, or if the battery is damaged or anything else, gets more clogged. Strictly speaking, what's happened is the electrodes are starting to get damaged, and so the connection with the electrolyte is getting worse. That's a whole nother talk. But the simple way to think about it is the filter is getting clogged and that resistance goes up. That 0.005 is for a pretty healthy battery. Some chargers will give you an IR measurement. I would not treat those seriously. Pay attention to your battery health. If you are flying electric power and you notice they're warmer when you land, or this is important, every time you charge, check the relative per cell voltage when you plug it into the charger. If when you land and you recharge, you're starting to see the 3 or 6 or 12 cells not all being within half of a tenth of each other, you're starting to have a cell go bad. That's the easy way to do it. But again, whole nother talk. So internal resistance clear? So last theory page, wire ratings. Wire resistance depends on cross-section. Of course, it depends on materials. This table is for copper wire. There are different formulations of copper. If you're down in the weeds of worrying what kind of copper you have, You're at the edge of optimization and this talk. All the math I'm showing you, just get the right table. All the math I'm telling you is valid for getting down to that last percentage performance. My conclusion is going to be when I get there, for most sport applications, this is just not critical. Airflow matters, insulation matters because how the insulation performs under elevated heats, et cetera. So I've done 10 wire gauges. You guys probably know bigger numbers are smaller wires. And it doesn't matter the number of strands. When they give you the gauge, it'll be the same total cross section. So this is the resistance per meter, the weight in grams per meter, and the sort of official safe continuous current rating, which we're going to now explore a bit. And there's a good table that I use in the link there.
There's a question.
John, is now a good time to ask another question?
Absolutely.
When a pack puffs, what's going on there?
The short version is that's hydrogen collecting in the cell. Now, why is hydrogen collecting in the cell? It's because of electrode damage, and the electrolyte is starting to come apart into its components, which includes hydrogen. So you can fill in why are there battery fires from there, because hydrogen and oxygen. Yeah, so we're going to get back to safety, and I'm going to not talk about it, but as long as you just raised it, these packs spontaneously combust. We've all heard stories. It's real stuff. Also, if you damage them, if you puncture them or they're creased or, look at your packs. I fly puff packs, and my metric is what I said. When I go to put them on the charger, if each cell needs to be within like 0.02 to 0.05, if I put it on one of them is a tenth different than the others, I'll charge it once and fly it again. If that happens twice, that battery is done for me. For non-critical applications. For critical applications where I'm really pushing the current, I won't even go that far. Puff packs are out.
John, there's a question about what gauge is servo wire.
Glad you asked. 22 gauge is standard standard duty. Like if you just bought a regular sort of standard size servo, it'd be 22 gauge probably. And the light stuff that you buy for light hand launches is 26. You can get heavy duty, which varies. Typically it's 18. I didn't do any cases with heavy duty for reasons you'll see in a minute.
I've gone lighter.
Well, for time is one of the reasons, but also for other reasons. Okay, so let's talk about a hand launch. So I really need to get my face out of the way here. I went to the bench and did some stuff. Now, this is not ideal. Like the ideal way to do this test, there it is, would be to put telemetry in an airplane or a recording device. And if anyone wants to go do that with me, I have the telemetry equipment. What I've done is I've just put a current meter in line while I wiggle the stuff. And you're going to say, that's not flight loads. And I'm going to agree with you. So then I put my finger on the elevator servo and I pushed really hard. Like I stalled the servo, and stalling the servo while it's static is different than stalling the servo while it's moving. And I did the same with my right flap. And I pushed so hard, I ripped the horn out of the flap, just to give you an idea. And you see that peaks at about 0.45 amps doing that. So if I had two flap servos near stall, I'd be pushing about an amp, regardless of what the rest of the system, which as you can see is kind of idling around 150 to 200 milliamps. So just getting intuition here for how much current are we drawing. So I say 200 to 1,000 milliamps. 26 gauge is rated at 0.65 continuous. So we're okay. You're going to be under 0.65 continuous. You're going to peak to an amp. Maybe you can imagine an amp and a half circumstance. And so you could say, well, let's go smaller than 26 gauge. And the problem would be that the wires are so small at that point that just the mechanical wear and tear of plugging things in and unplugging them and flying around and being flung by gorillas at 100 miles an hour, you start to worry about the robustness of the wire itself. And that's why you don't see lower than 26 gauge very often. The capacity, so that's a 500 milliamp hour pack. So I could run half an amp for an hour, right? That's how the math works. So for me, 30 minutes is a good safety margin. And of course, I'm running telemetry, so I know when to land. And I'm going to talk more about that in a couple of minutes. People sometimes fly 2S. If you do 2S to increase the voltage, you will get faster servos. And the way our digital servos are programmed, they will be faster and use more power. So I'm going to talk about I squared R losses in a minute. That doesn't help you here, even though you don't know what it is yet, because the things are programmed just to take more juice and use it. And the battery energy density is lower because you're kind of packing the good stuff ratio is lower with 2 cells. So there's nothing wrong with doing 2S, but it's not a weight optimization. And then the wires are really short. So I'm not even going to bother to do a wire resistance calculation because I know the answer for a 4-meter glider, which is coming up. And once I did that, I decided this wasn't worth the trouble.
John, we got a question. I'm not sure you can answer it. It says, what's the difference in current draw in a 10-minute flight window between push rods on a horizontal vertical tail versus pull spring?
Oh, that's a great question. And I could have answered that. I didn't think about it. If I'd gone back to the elevator and taken the tension off the pull springs, we could have looked at the drop. I didn't do it. We can definitely get that answer. What I'd really like to do, if I can get someone who's interested in, kind of helping out and playing along, is put some telemetry like in an old Snipe plus maybe this airplane or something similar. And then we could get much better data.
Let's put
This is
telemetry.
a F3J plane.
Got
It's
Steve,
Larry
you got-
Jolly's.
Steve,
Oh,
you got
sorry,
a
go ahead.
question? Steve?
Not really a question. I was saying I'd love to put that telemetry in my 3rd scale airplane and see what all 19 servos are drawing, and
We should totally do that. And
room.
yeah,
Yeah,
this
me too,
is
John.
this is Larry Jolly's B F3J plane as opposed to his A that he took to the 2004 Worlds. I'm kind of proud to own it, so that's why I said that. It's a something extreme, a racer extreme. 6 servos, older JR digitals. These are not the most modern, massive, high power wing servos we typically use. Same game. I'm just going to, I'm just kind of wiggling things around. You're looking at just over half an amp. And then I'm going, if I move the flap servos and nothing else, you see we got to an amp, just moving them with no airflow, right? So unloaded. Now this is static load. I didn't have enough hands. I should have got someone else to hold the camera. I'm pretty sure that if I had held back while the flaps were lowering, I'd have gotten another amp out of that. But given I was getting to near 2 amps and I've got 2 of those flap servos plus 4 others along for the ride, I'm going to call this between 300 and 4,000 milliamps. This is standard servo wire, so 22 AWG. Note that these connectors are officially rated at 3.5 amps. So we're only hitting that peak. I'm not too worried about the connector. If everything's healthy, if nobody's been wiggling the wire and flying this thing for a decade and plugging things in and unplugging and the wires are getting frayed, right? New connectors. I'm going to come back to that. Just to do the capacity math, this is a 3S lithium ion pack I made for it with a Castle regulator, and that's a 3400 amp pack at 11.1 volts nominal. So this is where the milliamp hour thing doesn't help me much because the Castle's running 5 volts. And so I really need to do energy. So to go to energy, just assuming we're running 1 amp average for easiness, the energy is, as I said before, current times voltage times time. So 38 watt hours. Then I can divide by voltage again to get amp hours. So it's 7,500 milliamp hours, 7.5 amp hours, which means I could easily fly this plane for 4 hours. And actually bench testing it, I could fly it much longer than that. But with high safety margin, 4 hours is the calculation. Clear so far?
Yeah, this is great. I'm loving this.
Okay. Oh, cool. 4 meter. So this is very conservative. Okay. So imagine a 4 meter plane where the outer aileron servo is 1.5 meters out. The inner one's 300 centimeters. Sorry for mixed units. Just to be obnoxious, I put the elevator and rudder in the tail to have 1.5 meter runs. And then the flap servos at 2/10 of a meter out. And then I'm saying that the nose, like the distance to the battery from the wing connector, is another 0.3. If you add all that up, that's 7.6 meters. Now, most people, when they're doing wings, will actually do shared positive and negative between the flap and aileron. Pluses and minus for that, but I'm kind of trying to do I am doing the worst case here. So I just said, suppose you run a 3-conductor wire to every servo individually. You have to account for the current going out the plus and back the minus, or vice versa, depending on how old of a physicist you are. So we got to think about 15 meters here of wire. Okay. So 15 meters of wire, based off that chart, is 2 ohms at 22 gauge and 5 ohms at 26 gauge. So this is a little sample problem of what would it be a good idea to put 26 gauge in my 4 meter, because it's an F5J plane and I want it to be as light as possible. So the power loss in the wire isn't too bad. 0.02 watts for 22 gauge, 0.05 watts for 26 gauge. If you turn that back into like capacity loss, like if you were trying to fly for a really long time, you're talking about, for the 26 gauge, losing 10 milliamp hours on a 5-volt battery. So again, a really not interesting amount of power loss due to resistance in the wires. You want to check voltage drop, because if you're running really long wires and they're really small and you've got current at, now in this case, remember, this is 100 milliamp per servo. So an idle servo, the voltage drop is insignificant. Now, if I didn't do the math here, but I think I've shown you enough that you could, if you had a stalled super high power flat servo that was pulling 3 amps, your voltage drop could be a lot more interesting. It could be enough to actually make the little brain in your digital servo lose its marbles. But for the purpose of thinking about battery duration, wire resistance isn't a factor. You could do 26 gauge, no problem. You'd save 25 grams. So not nothing, but if I take and say, don't do 100 milliamps, which is idle, take all 6 servos to an amp, now the wire loss is 5 watts, right? That's 1,000 milliamp capacity loss if you use the 26 gauge wire. So now you're actually talking significant flight time reduction and measurable heat in your wires. Now, if you really try to optimize down to 26 gauge or smaller, and then you like do a terminal velocity dive and pull flaps, you're well beyond what the 26 gauge can handle. But I just wanted to show you how you would do the math. So if you're doing a half scale glider with long runs, this is how you do the math. 22 gauge probably isn't enough for a glider that big, especially if they're very high powered servos. Okay, questions? Okay, let's talk about powered aircraft. The upper diagram is a sort of a loose schematic of how receiver power is made in most gliders, your Radian, a lot of your F5J planes. You've got an electronic speed control in the middle there. Again, I'm focusing on the top half here. It's providing, I didn't even draw the motor on here. That's funny, because I don't care. For this analysis, the motor battery is coming in, and there's a motor controller, which would go to a motor if I bothered to draw it. And then the input motor battery is also going to a battery eliminator circuit, which puts out 5 volts. That's actually programmable. You could program it to 6 volts. You could program it to 7.4. And then the ground goes to the receiver, and there's a throttle signal coming back. So that's why to hook your ESC up to your receiver, you only need the one wire. You've got plus, minus, and signal. I got another slide on this, but all these BECs have specs. One of the specs that it's hard to find this. So a quality company like Castle will give you a lot more than other companies will, but it takes more voltage into the BEC than it can put out. So if you imagine this setup with a 2-cell battery, and you turn the motor on and your voltage drops to 3.2 volts a cell because of internal resistance, as we discussed, you'd be getting 6.4 to that BEC. And if you put the output at 6, the BEC may actually fail, or at least lower its voltage. And Castle, the folks at Castle are good enough to tell you exactly how some of their BECs fail. And most companies, you're lucky if they even tell you any of this stuff.
John, for the uninitiated, can you explain what a BEC is, what it stands for?
Battery eliminator circuit, which is in the early days of these, when they were really problematic, we jokingly called them airplane eliminator circuits. So what happens? You're basically that actually takes us to the diagram below. You don't have to do it this way, right? You can use the motor to power the electronic speed control, which powers your motor, and then you can just put a receiver battery in. So then you don't need a BEC. And just as a note, if you want to do that, if you buy a ESC with a built-in, so electronic speed control with a built-in BEC, you don't want to hook that up to your receiver battery. So what you do is you take the little red wire out of the connector that goes to the receiver. You can cut it. What I like to do is actually pull it out of the connector and hit it with heat shrink so I can reverse the process. Then you have throttle signal and ground from the receiver, just like it's a servo now, to the electronic speed control, and you've got your battery in. So why would you do that? You do that if you need more duration, and you say, well, that motor battery is really big, but what if I drained the motor battery climbing? Or you need more current than the BEC can provide. More on that in a second. If you're nervous about the BEC and you don't really care about weight because the particular airplane is a slope plane, well, why would you have a motor on a slope plane? Ask Gary. Here's a key one. If you're flying an airplane without motor battery voltage telemetry and you're relying on your receiver battery telemetry, in this case on the top, it always reads 5 until it crashes. So if you're flying anything you care about, you really want to have telemetry wired to your receiver directly from the motor battery, so you know not to keep doing one more climb that takes your radio out.
John,
I think there are probably questions.
Yeah, question about the UBEC. What's a U?
That's probably a typo. Where does it say that?
Yeah, I could see that. Moose, question?
It's just something I see in my power planes, a UBEC, and I don't know what the U stands for.
I don't know that either.
Maybe universal? I don't know. Never heard of it.
Oh, there you go.
All these ESCs are configurable. You hook them into your computer. One of the settings you'll notice a lot of them have by default is a current limit for the BEC, where if the current to the receiver and all your servos exceeds a value, it will disable the BEC to save the ESC. So you probably want to make a choice about whether you'd like to save the ESC. You'd like to kill your airplane to save the ESC. And that in every receiver, every ESC I've seen that has that as an option, it is set to on and at a current limit that, anyway, check that setting. Okay, I should probably go faster now because I've got movies at the end. So just some, you guys can look at this in more detail, but I pulled stuff off of 3 examples from Castle because, like I said, they're good about giving specs. So, but even them, it's like, it's a 10 amp BEC. Well, not really. It's 5 or 7, depending on how many batteries you hook up to it. And it expects to have airflow. So that's cool. But what if my airplane's stuck in a tree with a servo stalled? No airflow, maximum current. Is everything still okay? I put this BEC Pro in here for bigger airplanes, and I use these in my helicopters because the helicopter servos really eat power. The other thing to note at this is that the good folks at Castle give you 2 output wires, and you're supposed to hook them both into your receiver. And it's not because of the wire gauge. They could have put bigger wire in. It's because the connectors are rated for 3.5 amps. And if they're going to give you a 20 amp BEC, it's a little silly to try to plug that through a small connector. This is an example that a lot of guys are flying like an F5J, and this is the BEC that comes with the new Radians. And notice they give a 3.5 amp continuous, which is nice and plenty for something like a Radian, even a night Radian. But the older E-flite ones didn't have that current capacity. Okay, moving along, I squared R. Now we're getting a little more esoteric, but it's something you're going to hear about, and it's something I think about for reasons you'll see. So let me take a high-powered situation. I got a 44-volt battery, which is a well cell in series. And now I've made the wire dark. So what I'm going to say is I do some magic to configure the motor and the ESC and everything in the throttle setting to do 2.7 kilowatts. So that's 60 amps at 44.4 volts. And the wire resistance in my example, I'm using 10 gauge wire in this example, and assuming a half a meter of wire. So there's about 12.5 watts of power lost in the wire. The power loss in the wire, as we said on one of the first pages, is current squared times the resistance. So if I were to say, you know what, I don't want to fly that helicopter or airplane on 12 cells, that's kind of crazy. I want to do it on 6 cells. That's 22.2 volts nominal. But I still want my 2.7 kilowatts. Well, now I need 120 amps. Okay, well, I need a bigger ESC for one thing, but you can go buy those. But now the wire itself, the same 10 gauge wire at the same half a meter harness length is discharging 50 watts just in the wire. And that's a lot. You're going to melt insulation if you run it for any amount of time. This is when people talk about I squared R losses, especially in wire, this is what we're talking about. But this happens everywhere. Anything that has to do stuff, the ESC itself has I squared R losses. The battery has I squared R losses. Those internal resistance values we're talking about, you may have half the internal resistance, but the current, the loss, the heating of the battery due to the current is twice as bad in this case as it is in this because of the I squared R. So why would you care? Not in your hand launch, not in your F3J, probably not in your F5J. On the left is a sport aerobatic heli. It's a Mikado Logo 600 for those of you who care. It runs 12 cell. I routinely peak it at 80 amps. Average current over a 5-minute flight is 40 amps. I keep the wire runs really short, and they're 10 gauge. On the right is a distance heli, and that has, it actually runs at a much lower current, but it has to run for over an hour. And it has a lot, the battery is a lot more complicated. So that pile of wires on the bottom and then on the right is what it takes to make that helicopter work, just to hook up all the batteries. Some things to note about that. That's 141 grams of wire in a 5 kilogram limit helicopter. So now I care about battery wire weight. Like I really care about wire weight. The other thing I want you to notice is on my sport heli that I like go to a fun fly and I'm there for 2 days and I'm flying till I'm tired every day. You cannot plug that in wrong, because if you plug those batteries in wrong, you have a problem. The one on the right is completely optimized for efficiency. Those bullet connectors are very low resistance. I had to optimize everything. It's incredibly easy to wire this wrong with catastrophic results. And I'm going to come back to this point now with safety. Let me pause for a drink of water and questions.
All good, John.
So hierarchy of concerns. Actually, I should have let Cliff write this slide, so I'll let Cliff edit me if he wants to. I think about it in terms of keeping myself safe, keeping my house and the flying field safe, and then not losing my aircraft. So personally, I'm worried about shock. I'm worried about burning myself. At the flying field and at my house, in terms of protecting those, I'm mostly worried about fire. For the aircraft, obviously fire is real bad. And the more common concern is for any reason you lose power to the radio. There's all kinds of other ways to have an airplane crash, but in the context of this talk, we're going to talk about loss of power to the radio. I'm not going to talk more about shock. This is not don't take this to the bank, don't go test this, but most RC systems are at 50 volts or lower. You'd really have to work at it to shock yourself at 50 volts. At 110 volts house wiring, you don't have to work at it to kill yourself. You just have to be a little unlucky. If you're in Europe at 220 and you get across it, your chances, it's not a question of being unlucky. It's more like 50-50, you're dead. And if you're in Europe, you'll notice that the plugs in Europe are all much more carefully shrouded than the ones at 110 in the US, just as a side note. If you're flying bigger airplanes and you get up 80 volts, 100 volts, start worrying about shock. Seriously.
John, quick question. What's the current rating of typical servo plugs or connectors?
3.5 amps. And I'm going to do more on that in a moment.
Thanks.
Okay, so let's talk about fire. So wires have resistance, as we've discussed. Connectors have resistance. If you get too much current, it heats it. If you heat it enough, it'll melt it. If you melt it well enough, you'll short it, and then the current will go way up because these batteries can do a lot of current. So here's a movie for your amusement. This is 22 gauge wire. What I did is I just took this is 3 conductor wire. I twisted the red and black together on the left and hooked up this adjustable current power supply to it on the right with alligator clips. Kapton tape is really good for hinges. It's also really good for electronics because it has amazing insulating capabilities and really good heat resistance. At 5 amps, I can't feel it getting hot. Now, this hasn't been sitting in a tree with a stalled servo for an hour, right? But just sitting here for as long as you've been watching, this is all real time. I'm not feeling anything. Okay, so I'm impatient. I just cranked this puppy to 10 amps, which is all my power supply will do. Now I can feel it getting warm. I think I'm going to put my finger back on it. Yep, a little cautiously, but it's actually just, I can feel that it's warm. It's not hurting me. But I let it sit here for a while and I've stopped putting my finger on it because, you can't see it well here, but if you were there, you would notice that I am making dents in the insulation that are staying. So at 10 amps, this 22 gauge wire is being damaged. Why am I doing this? I just want you guys to have some intuition for this stuff. When I was a kid and unsupervised, I used to make wire glow with a big power supply I had, and you learn a lot about what wire will and won't do. Wire will do amazing things. And so I'm testing the end there. You'll see why. I did this one second. The first one is coming up. You can really do a lot with wire. And so for operating conditions that we're worried about with our aircraft, you just don't have to think about it this much. I've done this whole analysis because I want you to know how to do it for when you get to extreme circumstances. But when we get to this business of shorting is a case we really have to think about in airplanes. Okay, so I'm going to do 2 more movies. The next one is 26 gauge. Same setup. I've twisted it on the left. It's not soldered, by the way, just twisted. Same power supply. I'm going to go slower here. And you'll see I'm a lot more cautious here, and that's because I filmed this one before the last one I showed you. So I was a little more tentative. Plus, it's smaller wire, right? So you see, I remind you that it's rated at 0.6 of an amp continuous. So I'm not even at the continuous rating yet. I'm touching it. It's room temperature. We're going to keep cranking it up here to 10 amps eventually. I highlight the fact that it's twisted on the left and not soldered. If you think about how a connector works, that's a crimp. And a crimp is better than a twist for conductivity and less good than a solder. As an aside, we don't solder crimp connectors because that wicks solder into the multi-strand wire, which then makes it stiff. And when it flexes, it will break. So crimp connectors have a crimp for the insulation and a crimp for the metal, and they're not designed to be soldered. If you want to, you could tin the wire, but you're not meant to solder them in those connectors. Even though the resistance would be lower, the break probability goes way up. Okay, so I'm at 4 amps now, and it's kind of not interesting, but I stopped touching it because I can feel it getting a little warm. Pay attention to the left where it's twisted. So it's almost 7 amps now. Are you guys seeing smoke? So it gets hot first at that
Magic
twisted
smoke.
connection. Now I'm starting to seal. Now the wire is going soft at 6 amps, and I'm going to stop playing with it and crank it up to 10. So this is way beyond what you're going to run with stalled servos in a dive on a hand launch glider, right? So I'm not showing you this because, I'm not showing you this either to say, go with microscopic, 30 gauge wire, nor am I showing it to you to be alarmed. I'm just trying to build some intuition here. But just for fun, 10 amps just cooks the wire. Okay, so note my little cart. You probably noticed this is not picking on Armstor. We're almost all flying these gumstick batteries, and they're really good batteries. They're tiny. They have a lot of capacity. They have a 90 sig current rating, which, do I believe that for running an electromotor? I don't know. I tell you what I do believe it for, that if you short it out, it'll give you 45 amps. So that was 10 amps on the left. If you had a shorted connection with one of these little batteries, you would well exceed 10 amps. I know this because I have I plugged them in wrong when I was using microDeans connectors, which I have stopped using, by the way. And I melted the solder off those connectors, which is why it stopped before it caused a big catastrophe. Quickly. It wasn't like it sat there for half an hour and melted the solder. I made the mistake, burned my finger, and melted the solder all as fast as I could think what happened. Okay, 3.5 amps. What you got here is a servo connector. I used heavier wire. This is, I don't actually know, but I'm going to guess this is 18 gauge wire. I soldered this in because I didn't want this to be a problem. I just wanted to put some current through a connector. So the left is a servo end. The right is your typical female end that you'd get off of a extension or something. But I cut the shell off of it, that female shell, just so we could see what was happening and so I could touch it. And here's 4 amps. That's the rated current. I'm not really feeling any heat, but I want to remind you, these are brand spanking new connectors out of the bag. They haven't been plugged and unplugged 100 times. Any questions? Gary, am I okay if I'm going 5 minutes or 10 minutes over? Or do I got to wrap this up?
Yes, sir. This is great. Keep going.
Okay, so we're gonna crank this up, and I'm tempted to fast forward it, but it's not that much longer. And anyway, I'm fast forwarding it myself by cranking it to 10 amps. So this is well above. It's not 10 times the rating. It's 3 times the rating, 2 times the rating. And then I am going to touch it and regret it, just to give you a preview of what's about to happen. These are just the regular off the shelf. They're not gold plated, but they are new, which really has a factor in how much heating they're going to get. I know I'm gonna, come on, John. I know I'm fast forwarding it. So basically, I'm testing the wire. The wire is totally fine. This is 18 gauge wire. And somewhere in here, I touched it. Where did that go? Touched it at, I'm sorry, I skipped that. At 7 amps, it was hot enough that I decided not to touch it anymore. Sorry, so if it's rated for 3.5 at twice the rating, it's too hot to touch. Got it?
Mm-hmm.
Okay, let's get to loss of receiver power. So all those fire things are, you break a wire, you short a wire, you crash. They're real concerns. You need to think about them before you get too crazy optimizing your wire size and everything. Okay, this is that same battery capacity curve. If I do an example of a DLG again, cruising at 200 milliamps, then I pull full flaps at speed. I call it an amp. I think 2 amps is easily achievable, but my example is 1 amp. Keep things simple. If I've already flown 70% of the battery down and I'm at 3.6 volts in cruise mode, just cruising along, and then I go into a dive and I yank flaps, according to this curve for this battery, which, batteries vary, that drops my voltage to 3.45, which is below the rated minimum voltage to keep the little CPU running in your FreeSky GR6. So many of you have experienced this. I know I've experienced this. If I set my alarm to 3.6 and then I'm at the end of a heat and I've skied out and I'm so stoked and I decide to dive like a madman and pull flaps and suddenly my battery alarm goes off, this is what's happening. We already talked about the regulated BECs. They have their own limits. They behave differently than batteries. Some kinds of regulators fail catastrophically. Some fail gently. So let me pause for questions here, and then I'll do conclusions and then questions again.
So John, are you recommending a regulator?
Depends on the airplane, not for hand launches. I think the hand launch setup we've all sort of come to know and love is fine. On the other hand, people talk about what to set your alarm at. Should it be 3.7 or 3.6? The problem with 3.7 is the curve is so flat, you really lose a lot. I set mine at 3.6, but I look at the screen every time I come in from flying. And if I'm at 3.6 or 3.7, I'll just stop and recharge. If I hear an alarm, my 3.6 alarm go off, no matter what's happening, even if I'm about to win the international, I will land the plane. But I don't think you need a regulator. For bigger airplanes, I like regulators, mostly because it's just, it's kind of hard to get. Nickel metal hydrides are kind of a pain in the butt. Lithium ions and lithium polymers are actually kind of nice to deal with because it's really easy to know how much you've discharged and charged them, whereas nickel metal hydrides have all kind of false peak. So the reason I recommend a regulator for gliders at larger sizes is simply because the batteries are so much more convenient. Does that answer your question?
Sure.
Okay, so conclusions. Well, I've made a lot of them as I go. In our conversation on Discord that got all this started, like if you just do what everybody else is doing, you're fine. 22 gauge off the shelf, what the manufacturer sells you is gonna work. Small planes, 26 gauge is gonna work. The one thing I would say as an exception to what most manufacturers tell you is just fine, is if you start flying big modern servos on a 3 or 4 meter plane that you intend to go fast with, even just goofing around, diving and pulling flaps on a not a race plane or something, you're really pushing the edge of the connector from your battery or your regulator or whatever. So one of the things I am re-plumbing my Explorer that I had so much fun with on Saturday. And that will be getting 2 power connectors to the receiver based on the testing I did to make this presentation. This battery drop thing is real. It is short circuits and broken wires are a good way to lose a plane. Battery drop from internal resistance is a good way to lose a plane. If you're using a BEC, whether it's a standalone one or part of a ESC, read the manual, check the settings, make sure they're what you want them to be. And I've said it 1,000 times, if you're flying a sport plane or you're flying even a competition plane that you fly all the time, count on wearing it out.
It was
and
good.
Count on putting it in a tree and stalling a servo. And think about all these things that can go wrong and give yourself some headroom. And then my last point is all of this stuff is calculated. If you want calculable, if you want to go for an AMA record and you really want an optimized plane, everything you need to know how to do that is in here.